Hello friends, is your AI ML infrastructure struggling to keep up? Discover the ML infrastructure and the power of adaptive load balancing in this short video. Let's understand the most common high-level design for a network optimized for machine learning. We have at the very outset a front-end fabric. This is where users and applications interact with the ML system. It could include web servers, APIs, or any other interfaces. This is the typical spine leaf architecture. Border leaf switches connect the front-end fabric to the rest of the network, handling the routing and filtering of traffic. Spine switches act as the backbone of the network, and leaf switches connect to the actual computing resources used for ML tasks such as GPUs or specialized processors. Now, the second part is the backend fabric. This is where the heavy lifting of ML happens. This is where you have your servers with GPUs. These are powerful servers equipped with graphics processing units, specifically designed for parallel processing needs of ML training and inference. And also we have infrastructure dedicated to training ML models. This could include specialized hardware and software for distributed training, data preprocessing, or model optimization. And then we have storage and inference network. We all know data is king. Storage is a critical component of any ML infrastructure. The network design should prioritize fast and reliable access of data. Inference at scale. The network should be able to handle the demands of inference workloads, which can vary significantly in terms of volume and latency requirements. We must have flexibility. The architecture should be flexible enough to support different types of storage and inference solutions. And this can allow you to choose the best option that suits your needs. So what are the key benefits aspects of AI/ML infra? The first and foremost is uniform link utilization. In a spine leaf network, it is very important to ensure the traffic is distributed evenly across the links between spine and leaf switches. This is where features like ECMP help. We must have a lossless behavior. The network should be designed to prevent packet loss, even under high traffic loads. Features like ECN and PFC comes to the rescue here. Factors like the number of switches, the distance between them, and the required data rates will influence the choice of topology and optics. This also matters for AI/ML infra. The network should be designed to support multi-tenancy. This provides isolation between different tenants to ensure security and performance. Last but not the least, we must have provisioning and automation. Automating our provisioning of network resources can simplify management and reduce the risk of errors. Now, ML training requires iteration-level atomicity. For ML training across GPUs, a job is divided into multiple iterations, and each iteration involves several steps. The first step is initialization. This is where GPUs prepare data and resources for computation. Now, computation, this is where GPUs perform computations on their assigned portion of data. And then we have data transfer. Intermediate results or gradients are then transferred between GPUs, which is shown as green and orange lines. This might involve direct GPU to GPU communication or transfer to the host CPU. We also have aggregation within GPU. Each GPU processes the received data, potentially performing operations like reduce scatter, which is reducing data and scattering across multiple GPUs, or all gather, which is gathering data from all GPUs to each GPU, which is shown in purple here. But the most important aspect is the sequence, which is initialization, computation, data transfer, or aggregation, represents a single iteration. And this is repeated multiple times till the entire job is complete, all the training job is complete. Crucially, if any iteration fails, for example, due to an error in computation or data transfer, the job halts and iteration is repeated. Today's powerful GPUs can handle massive amounts of data. We are talking about 800 gigabits per second. This can easily saturate network connections. However, traditional load balancing methods can inadvertently create bottlenecks by unevenly distributing the traffic across network links. This means some connections get overloaded while others sit idle. This can ultimately slow down the training of your complete AI workflow. Now, this condition can happen at leaf or spine levels. the traffic from several leaves or several leaf switches through the spike may be directed to the same leaf. With finite capacity and possibly a single spine to leaf downlink, flows can oversubscribe the interface, resulting in buffer exhaustion, congestion, or drops. This is where features like ECMP helps you load balance your traffic flow. Now let's understand why your ECMP might be failing you at times. We know that the distribution of a given traffic flow across one of the ECMP leg is based on a hash function. Hash function generates a hash based on n tuple, primarily comprising several fields of L2, L3, L4 packet headers. The many-to-one mapping between one or more hash value can cause unbalanced traffic distribution sometimes. And this unbalanced traffic distribution would create an overload condition for child links. Not to mention, if the unbalanced child link is persistent, the only recovery may be to add or remove legs of an ECMP path. There's a router R1 which is using a hash function to distribute traffic across multiple next hops R2, R3, R4, R5. The hash function assigns each packet to a specific hash bucket, which then determines the next hop for that particular packet. In the ideal case, which is equal flows and equal traffic rate, the hash function distributes traffic evenly across all the next hops. This results in optimal load balancing. But what happens if the hash function is not well designed? It can lead to uneven traffic distribution, where some links become overloaded while others remain underutilized. This can surely cause performance bottlenecks and network congestion. If we take another example, a single large flow or a fat flow can also disrupt load balancing. If a significant portion of traffic belongs to a single flow, it might all be hashed to the same next hop. This will overload that link and cause uneven distribution. This is where adaptive load balancing comes into picture. It helps prevent network congestion in AIML infrastructure. Instead of just relying on simple hashing to distribute traffic, ALB intelligently monitors network links and dynamically adjusts how data flows are routed. This ensures that no single link gets overloaded, maximizing efficiency and preventing slowdowns of your AI jobs. Even with very demanding workloads or unexpected spikes in traffic, ALB can keep your network running smoothly and in turn would help you to avoid any condition in AML load workload training. Now with Express ASICs, we achieve adaptive load balancing in our networking hardware. These chips have built-in intelligence to constantly monitor network traffic and make real-time adjustments to ensure smooth and efficient data flow. Let's understand how it works. The first and foremost part is traffic analysis. The Express ASICs analyzes incoming data types or data packets, identifying different flows and also measuring their bandwidth usage. Based upon this analysis, the ASIC automatically adjusts how traffic is distributed across network links. This also prevents any single link from becoming overloaded, ensuring that data can move quickly and efficiently throughout the network. The selected buckets can be maintained per ASIC or per line card level. With the Express ASIC, we achieve adaptive load balancing in our networking hardware. These chips have built-in intelligence to constantly monitor network traffic and have real-time adjustments to ensure smooth and efficient data flow. Now think of it like a smart traffic management system for your complete network, which prevents bottlenecks and keep the data flow smoothly, especially important for your demanding AI/ML workloads. Thank you.